So today we are going to be talking about the basics of forces. There are two types of forces, contact forces and forces at a distance. In this case, we're going to be talking about contact forces, that is when one object directly interacts with another object through touching. The equation we use to describe force is force equals mass times acceleration. That means that the units of force are kilograms times meters per second squared. To simplify, we call kilograms times meters per second square newtons. The units of acceleration, as you probably know, are meters per second squared, and the units of mass that we use are kilogram. Also, it is important to note that force is a vector, meaning that it has direction, as opposed to a scalar, which does not have direction. How much tension must a rope withstand if it is used to accelerate a 960 kilogram car horizontally along a frictionless surface at 1.20 meters per second squared? We know that the equation to describe force is mass times acceleration. So then we have all the things we need to just plug directly into this equation. 960 kilograms times 1.20 meters per second squared. Next, we write this as 1,152 kilograms times meters per second squared. Now we know that kilograms times meters per second squared are the same as newtons, so we rewrite that along with the correct number of sig figs and get 1,150 newtons. So for our first problem, we're going to do a 20 kilogram box is at rest on a table. Draw a force diagram and calculate the gravitational force and normal force acting on the box. So first we're going to draw a dot to represent the box. Then we're going to draw a downward line with an arrow at the end to represent a vector, label this mg. Then we're going to draw the normal force, which is opposite of the gravitational force, and label this Fn for normal force. Now, because we know the box isn't moving, because the problem says it's at rest, we know that the force normal and the gravitational force must be equal. Because after all, if a box is stationary, all forces acting on the box must be equal. So we know the gravitational constant on Earth, 9.80 meters per second squared, and the weight of the box, or the mass of the box, which we know is 20 kilograms. Using this information, we can solve for the force of gravity on the box, and because we know normal force is equal, we know that they will both be 196 kilograms times meter per second squared. And if you remember from the previous part, we know that kilograms times meters per second squared are the same as newtons. So the final answer is both normal force and force of gravity are equal to 196 newtons. We are going to solve the problem. Draw a force diagram for a 10 kilogram box being pulled upwards at 30 degrees above the horizontal with the force of 100 newtons. We are also going to calculate both the horizontal and the vertical vector. First, we are going to draw a line mg to describe the force of gravity on the box. Then we are going to draw a line 30 degrees above the horizontal and name it force pull. Next, we are going to draw both a horizontal line and a vertical line. The horizontal line can be described by force pull times a cosine of theta, whereas the vertical line can be described by the line force pull times a sine of theta. We will write these labels by both of these lines. When drawing force diagrams, it is always important to make sure everything is labeled in order to avoid confusion in the future. First, we're going to calculate the force pull times the sine of theta. So when we get our calculators, we'll say 100 times the sine of 30. We should get 50 newtons. Next, we're going to calculate the horizontal vector, which we can write as the force pull times the cosine of theta. We'll plug this into our calculator as 100 times the cosine of 30, and we should get 86.6 newtons.